are ahead of time. So, good morning, everybody. Thank you for coming. It's a pleasure to have again here Professor Sheldon Glashow and Professor Wilczek. For a physicist my age, it's kind of weird to have to introduce these two persons in our mind are legends of the standard model of particle physics in general. I'm an experimentalist myself, and I did my thesis on charm particles in the 80s when everything was had already happened in a way. So the gene mechanism was sort of revelated truth for a guy like me. And in fact, I thought the famous gene paper in which the fourth one was postulated, I thought it was the first time it was postulated. But now you had a paper with Bjorken in the middle of the 60s already talking about possible fourth quark. But and in fact, in that paper, it was already implicit that this quark could avoid the famous flavor-changing, strengthness changing, in that case, neutral currents. It was made much more explicit in this gene paper. The name of Sheldon Glashow is spread all over the standard model with contributions here, critical contributions here and there. You know that the Nobel Prize was mainly awarded for postulating the symmetry group of the electroweak part of the standard model, that is famous SU2 cross U1. But there are contributions from everywhere in the right moment, in the right place. One of the things which is nice of both Sheldon Glashow and Frank Wilczek is they were close to experiment, to the physics of the time, and saw the things in advance. Long time ago, in fact, I met a young theoretician who thought that the standard model was discovered the same way it is taught nowadays. So in his head, somebody said, well, what would happen if we impose local gauge invariance to the Dirac equation? Here comes the photon, here comes QED. So now let's try a bigger group, SU2. We combine with U1, and here you have the electroweak part. And then the next obvious step was U1, SU2, SU3, and what? Well, it wasn't that way. It wasn't that way. It took physicists of the caliber of a person we have here to realize what was important in every moment. And so Sheldon Glashow put the contributions just in the right moment. And in fact, well, if I could say, there was a problem, we all know, with the mass, how to introduce the mass. It was a tricky thing. It was solved by the Higgs mechanism. But remember, the Weinberg paper is called a model of leptons, not a model of the electroweak theory. And the reason is that at that time, the hadron pair was such a mess that he decided to put aside hadrons in the electroweak theory. But the solution was around. With the gene paper and with the concept of quark, it was almost straightforward to combine both things, the leptonic part and the hadronic part, to produce the electroweak theory. And he was, as I said, very close to experiment, right? And this is also the case for the contribution of Frank Wilczek. It was not only, he was awarded the Nobel Prize not only for this, at those time, difficult computation of the beta function of QCD. It was much more than that. Both the groups at Princeton and at Harvard realized that this was important. And some people don't know that a couple of Russians in the middle of the 60s computed the beta function for a sort of theory, of QED theory, but with massive gauge bosons. And this Russian found that factor in the beta function was negative. And they concluded that this was extremely undesirable. And then there was another Russian a few years later that computed the beta function for SU2. And again, he got a negative sign and nothing happened. And it's also well known that Toft had computed, according to him, or we believe him, already beta function. But it was the genius part of the contribution of Frank Wilczek and the people both of Harvard and Princeton to relate that to now famous experiments that took place a few years before. These were the SLAC MIT experiments in which leptons were scattered off protons. And then what these experiments observed was that the protons seemed to be composed of little balls which seemed to be free. But the story is longer than that. There is Bjorken and Feynman in the middle, with the Bjorken scaling, in which he realized that instead of two variables, the scattering could be described by just one, the ratio of both, and this implied a theory. But even with this simplification, the point was, in fact, that they saw the importance of this negative sign in the beta function. They saw that that could explain, and now we call that asymptotic freedom, that could explain why these SLAC MIT experiments could see free particles in something which was a very strongly bound system. Again, I'm saying that because nowadays it seems that I wouldn't say experiment is going one way and theory another, but there is a sort of decoupling which is very unfortunate, according to me. And I finish here with the famous sentence of T.D. Lee, who said, "Without theorists, experimentalists falter." Falter means hesitate, fluctuate. But without experimentalists, theorists drift. And I think some theories are drifting way too much these days. So hopefully we will come back to these nice 50s, 60s, and 70s, and we get experimental theory closer. So thanks again for coming here. Now, the layout of this meeting is that both Professor Sheldon Glashow and Frank Wilczek will give a talk, and then we will have some time for questions, in particular from young people. And that's it. Thank you.
Okay. Thank you. Whoops. Is this thing working? Yes. It's always a great pleasure for me to be here in Valencia. I've been coming back every year for as long as I can remember, and I love your city. And let me get to a place where I can see the screen too. I'm going to give a historical talk going back, yes, to the 70s, to the 60s, even to the 50s, briefly, just to tell you how exciting things were. By the way, I agree fully with the remarks that theory and experiment should be together, and I've always lived cordially with my experimental colleagues. So let me go backward a long way. I went to the Bronx High School of Science in New York. I went to Cornell University. Then I got my degree from Harvard, technically in 1959, but actually in 1958. And let me just jump ahead to my advisor, who is roughly 100 years old today, unfortunately passed away, Julian Schwager. And he had a lot of students in my day. I was the last of 10 people to ask him for a thesis subject, and the only thing he had left was the idea of unifying weak and electromagnetic interactions. So he said, go unify. And so I wrote a thesis, and by 19 58, I had completed it. And this was what it said at the beginning. It's a quotation from Galileo, which you can all read because I'm sure you can understand Italian, but it more or less says that the poetic imagination comes in two varieties. Some people are good at inventing fables and others are stupid enough to believe them. Well, that's a vague translation. So I wrote my thesis, and from my fable, otherwise known as my thesis, I have a few quotations. So this is from my thesis of 1958. What good is a theory of weak interactions without a sensible theory of electrodynamics, I said. A fully acceptable theory of both interactions may be achieved only if they are treated together. And then, we need a large mass splitting between the charged bosons and the massless photon, and hope that this might be accomplished without the sacrifice of the conservation laws. Well, that was what Steve Weinberg would show us how to do quite a bit later in 1967. Okay, so then my plan was to spend a year in the Soviet Union, but it got shot down. Well, more precisely, the U-2 got shot down, and I was unable to get a visa. So I found the prize-winning group that we've been talking about in Copenhagen. On my alternative to going to Russia was to go to the Niels Bohr Institute. And the group, of course, is SU2 plus U1. And quoting again from my paper, which I submitted in 1960, just as I was leaving Copenhagen and going to Caltech. I wrote, the simplest partially symmetric system exhibiting all known interactions of leptons, both weak and electromagnetic, has been determined. It requires the existence of at least 4 vector boson fields, including the photon. And according to my informants, it was this paper and only this paper that justified my Nobel Prize that I shared with my high school friend, Steve Weinberg, and Abdus Salam. Another interregnum, went to Caltech as a postdoc. I couldn't get an assistant professorship, so I left after a year, went to Stanford University, got an assistant professorship. Professor Shipp was kind enough to tell me that under no circumstances would I get tenure at Stanford, so I quit, and I went to the University of California at Berkeley. 1 year at Caltech, 1 year at Stanford, 3 or 4 years at Berkeley. On sabbatical in Copenhagen, I met up with James Bjorkane, but we wrote a paper together, which you refer to, and we said, a new quantum number charm is violated only by the weak interactions, and our model predicts the existence of many charm particles. We were not smart enough to point out that we could solve the problem of strangeness changing neutral currents at that time, although implicitly we did. And it's interesting that B.J. Bjorkane refused to sign this paper with his ordinary name of James D. Bjorkane, which is how he signs all papers. He didn't want anyone ever to know that he had written something so stupid as this paper, which was called Elementary Particles in SU4. So he spells his name that way, on the paper, so it's not on his list of publications anywhere, with the line through the O and all that. Then we jump off. Now, this is 1970. The previous slide was 1964. 6 years passed. Nobody else talked about the possibility of suppressing strangeness changing neutral currents until it was Iliopoulos, Mayani, and myself. We had a wonderful year together, scuba diving and doing things like this. The conventional theory of weak interactions cannot be extended to a gauge theory without contradicting experiment. These are all quotes from the paper. because the neutral boson leads to Stratius changing decays involving neutral lepton currents and delta S equal 2 at order G. In our case, with the charm quark, these difficulties are absent and the electromagnetic theory can be extended, the electroweak theory can be extended to describe all known particles. That was in 1970, 3 years after Steve Weinberg had done his magnificent trick and introduced the Higgs boson into the SU2 cross U1 theory. Jumping along, this is a digression, and because this happens trying to be more or less temporally ordered. This was 1974 with Howard Georgi, and we wrote our Unity of All Elementary Particle Physics paper. This was where we introduced SU5. Howard would later introduce SO10, and Steve Weinberg and others would point out that the mass scale of SU5 could be predicted from your work, basically, and we expected that the proton decay would be seen imminently, that we would learn that we are all, after all, radioactive, but that didn't happen. I'm sure we are, but we haven't yet established the scale of our radioactivity. A series of hypotheses leads inescapably, this is quoted from the paper. The SU5 is the gauge group of the world. It is a subgroup of O10, so I'll stick to that. That all elementary particle forces, strong, weak, and electromagnetic, are different manifestations of the same fundamental interactions. The uniqueness and simplicity of our scheme are reasons enough that it be taken seriously. And it was taken seriously, and I still believe that this thing, which is called grand unified theory, unfortunately, is probably right. And I think Frank also believes that ultimately something like this has to be shown to be right. But meanwhile, the original theory was shown to be wrong, unfortunately. Then there was charm. Was charm ever going to be found? And it was. And the remarkable announcement was November of 1974. I was woken up by Sam Ting, who said, "Come to my office immediately," which I did, and he told me all about this discovery of the J particle. I told him I have no idea what it is, but I'll think about it. And I went off to Harvard. He was at MIT. And at Harvard, I got to my buddies, and Howard Georgi and all the rest, and I said, I heard something tremendous. And they said, we heard it too. But they had heard about the discovery of the psi from California. So we put things together quickly, and Alvaro and I wrote a paper immediately saying that we argue that the newly discovered narrow resonance at 3.1 is a bound state of charm quarks, charmonium. The crucial test of this notion is the existence of charm mesons near 2 GeV. That was in an early January Physical Review, first issue of 1975, and there were 10 other articles. You had one too, if I remember, and most of them didn't quite have it straight, but we did. So that was bound charm, and the question then was, where is open charm? Where is charm? Because not everyone believed this. My thesis advisor had written a paper saying it was something which it certainly was not. My collaborator, Luciano Maiani, with whom we wrote the Jim paper, was convinced that it was something entirely different. He got it all wrong, but you got it more or less right. Is charm found? Well, charm had been found by Nick Samios in a beautiful bubble chamber event, which nobody believed. We wanted to see lots of charm particles, and that took a long time. And finally, with Howard and Alvaro, we wrote another paper a few years later. It was in '76. A long story associated with that, and one of the Gerson Goldhaber was one of the collaborators who found this particle, and I had in April of that year, I had gone out and insisted that he look more carefully and that he do this and that and find the particles, because it was getting pretty embarrassing for him, not for me. And 2 weeks after my harangue, they reported the discovery of charm particles, and we all lived happily ever after. Now, that was basically all I had to say about history, but then, of course, other things happened as well that I wasn't responsible for. There was a third family of fundamental fermions emerging. They were from the tau lepton. It began with the tau and it ended with its neutrino, but between those 25 years we got the third family, with the top and bottom quarks in between. CP violation a la Kobayashi-Maskawa, solar neutrinos posed a problem. Atmospheric oscillations were reported in an extremely exciting conference in 1998 that I had the pleasure to attend. It's one of the only physics conferences I went to where the announcement by the Japanese group that they had discovered atmospheric oscillations was a tremendously exciting response. And it had been 19 years since I had suggested that there should be atmospheric, or people should look for atmospheric oscillations. And 19 years later, they were found. Snow, together with Super Kamiokande, solved the solar neutrino problem. In 2001, the Standard Model reigned supreme, and the Standard Model still reigns supreme. One last slide, perhaps. En route to the Standard Model, there have been a number of Nobel Prizes, and I just list here quite how many there have been. I probably left a few out. Did I include yours? You got it in 2004. You're right there. All kinds of prizes were awarded. And one last slide. After all, it is the 21st century. Did anything happen yesterday? Well, not yesterday, but there was, at the top I put the transient mention of superluminal neutrinos because I had a lot of fun shooting that incorrect discovery. Sorry, it always happens to me. It always happens to me in Valencia. It happened last year as well. Where are we? Higgs boson was found. Gravitational waves were discovered. Both of those things quite recently. The new science of gravitational wave astronomy is born, and it's doing more and more exciting things. The third event was just published just a few days ago. All's quiet on the LHC front. It's not clear that LHC in its present form is going to find anything exciting beyond what it already has done, but one can hope. Higher energies are still more or less a dream. CERN is planning to build a large machine, maybe by 2030, more likely 2040. And the Chinese have a similar idea, but that's far, far away. There seems to be no need for more than 3 active neutrino states. The evidence for, at least my view is, the evidence for sterile neutrinos has died away. Dark matter and dark energy remain mysterious, but I'll let Frank talk about that. String theorists, of course, continue to do whatever it is that string theorists. Thank you.
I propose to delay the questions after the talk of Frank Wilczek.
Thank you very much. It's very nice to be here. Getting to be a habit, which I intend to continue coming back. So I'm going to talk about projects which are ongoing, so they're not, this is looking in present and looking forward, but they are very much in the spirit of things that have experimental consequences, where we try to augment reality, not virtual reality, but augmented reality. So I'll talk about two specific things, axions and anyons. I hope in the question period, someone will ask about unification of families, which is work that we're doing right now with some physicists at Valencia, which continues in the spirit of unification that Professor Glashow mentioned and suggests some very interesting experimental possibilities as well. So axions. What are axions? So few aspects of experience are as striking as the asymmetry between past and future. Okay, we remember the past, but only guess about the future. We get older, not younger. And if you run a movie of everyday life backwards, it doesn't look like everyday life. So here we go. This is something you won't see every day. Of course, this was a movie of a building being exploded and going down, run backwards. But if you run it this way, if you run it backwards, and if you examine very, very closely the events that were going on, you'd find nothing that violated the laws of physics. It would be very strange. The ground would be rumbling for some reason with a lot of dust on it, and it would kick up. But the laws of motion would be perfectly obeyed. That's what's called time reversal symmetry. And that has been a notable property of the fundamental laws of physics for centuries, starting with Newtonian mechanics, continuing through general relativity and quantum electrodynamics, Maxwell equations, everything, quantum mechanics. None of these revolutions in physics upset the time reversal symmetry. Very, very strange, because as I mentioned, it's not something you need to describe everyday life, and yet it was this funny feature of the fundamental laws. Why? It only makes trouble, in fact, because you have to explain why, although the laws are symmetric, the world isn't in its appearances. Now, those of you who have small children, or have lived through knowing small children, or have been small children, know that it's always possible to keep asking why. Why? I answer you, and you can say, whenever I answer, you can say why. Here, if we ask why the laws have that symmetry, it's not clear that there would be a fruitful answer, that was a good question. It just might be a fundamental feature of the world. It might be rock bottom. Eventually, when you keep asking why, you have to say, that's just the way it is. However, in 1964, Cronin and Fitch, in a famous experiment, in a subtle effect in K-meson decays, showed that there is actually some small violations of this time reversal symmetry. Strictly speaking, they discovered CP violation, but CP violation is widely believed for good reasons to also imply T violation. And now we also have direct T violation. So T symmetry, this time reversal symmetry, is not rock bottom. That answer, well, that's just the way it is. That doesn't work anymore. Not even quite true. Why? So why do the laws have that feature? Now we know it is a good question. And we've almost nailed it as a consequence of our profound understanding of the laws of physics. The basic sacred with an asterisk, because nothing is sacred, but principles that seem to be very, very well established and tested in many, many ways on which our understanding of the world is based, relativity and quantum mechanics and local symmetry, those sacred principles are very, very powerful when you put them all together. And when you put them all together in the framework of the standard model, you find that there are exactly two possible sources of T violation, just as a kind of accidental consequence of the other symmetry, of the other principles. You find that the possibilities for violating time reversal symmetry are quite limited. One of them beautifully explains what Cronin and Fitch observed and a lot more. This is the so-called Kobayashi-Muscala theory of weak mixing angles, technically. The other is a possible coupling among the colored gluons of QCD, the so-called theta term, and experimentally there are just constraints on that. It doesn't happen. So, why? We're getting deeper answers and making progress, but we haven't yet got a fully satisfactory picture. Over the past, but it's become much more specific and pointed, why does this particular coupling not exist? So over the past 40 plus years, there have been several attempts to explain it, but only one has stood the test of time. That is, we promote the unwanted term, which comes as a coupling constant within the framework of the standard model. We promote that number to a field that can have its own dynamics and evolve in time. And if you do things right, you can set it up naturally so that that field will want to, for energetic reasons, evolve towards zero. Now, in the framework of modern physics, all fields are associated with particles, and this is no exception. The field that you need is made of a new kind of particle, which I named the axion. I named it the axion because I knew there was a laundry detergent named Axion, and I loved that name. I thought that should be a particle. It sounded just like a particle. And then it turns out that this particle cleans up a problem with the axial current. So it was a natural thing. I mentioned the axial current, but not the laundry detergent, to physical review letters, and so it got through the editorial process, and now it's become the standard name of this particle. So, do axions exist? Does this line of inquiry, starting with why is time reversal symmetry a good property of the fundamental laws, even though we don't need it for the description of experience, we don't know for sure. But in recent years, the stakes involved in this question have risen considerably. We can calculate, because of our very successful theory of matter, we can calculate with some confidence what happened in the early moments of the Big Bang, and we calculate, in the case of axions, they could produce in great abundance and survive to this day. The relic axion gas, which pervades the universe, according to these calculations, has properties consistent with the observed properties of the astronomer's mysterious dark matter. Let me quickly remind you what dark matter is all about. It's firmly rooted in observations. People, when they study galaxies, and of course the dark matter is not dark, it's just invisible, transparent. We don't know what it is. It interacts very weakly with all ordinary kinds of matter, including light, so it's been very difficult to study. But it does exert gravity, and that's how we infer its existence. And when you study the motion of the kinds of things we can observe, gas clouds and stars, rotating around galaxies, you find that there's not enough gravity to keep them bound unless there's an extra source of matter. And that's shown here, the difference between the observed amount of stellar and so forth matter and what you need to keep the particles moving properly. There's a beautiful smoking gun showing the existence of dark matter. This is the so-called bullet cluster of galaxies. There are two clusters colliding, and you can compare the distribution of matter in things that are luminous and things that we can observe with telescopes. So stars and gas clouds and things like that. That's the red. And the mass distribution of these colliding galaxies is different. There's extra stuff, and the explanation is as these galaxies pass through each other, the ordinary matter has significant interactions, non-gravitational interactions, so it kinds to stick together and dissipate energy, so it can stop, whereas the dark matter, which is much more weakly interacting, keeps moving, and that's what's observed. So, the bottom line of all this is that if axions exist at all, they must contribute to the dark matter, and plausibly, they dominate it. A very pretty picture, and suggests that out there in space, there's a specter haunting the universe, the specter of axions. Several clever they're difficult to observe, these axions, because they interact very, very feebly with ordinary matter, but several clever strategies for detecting them have emerged. It won't be easy, but many determined people are at work to do the observation. This is the Center for Axion and Precision Physics at Korea, and that's specifically devoted to searching for axions. There are many efforts around the world. Let me just give you a flavor of them. The basic idea of several of the searches is you have these axions, and you can predict in considerable detail their properties, if they're going to do what they're supposed to do in addressing the fundamental problems. And among the rest, they have a coupling to two photons, very feeble, but not zero. And if you let one of the photons be an intense magnetic field, you can convert an axion into a photon and then see the photon. So this is a microwave cavity. You make microwaves, and the details are very, very tricky because the signal is so weak. You have to make sure that other sources of noise don't get confused with this. But that's the basic idea, and people are at it. This is another idea, which I showed just because of its elegance. This is, again, if you have a magnetic field and the axions in the background doing their thing, they change a magnetic field at low frequencies into another magnetic field, an AC magnetic field, which can be detected by superconducting technology with great sensitivity. So altogether, there's hope. And another very, very clever idea is that axions can form halos around black holes. And now, as we're learning more about black holes, if they really have these kinds of atmospheres, if black holes really do have hair, they will, if axions exist, they'll have an axion atmosphere, and that can change their properties. And as we observe more about black holes, we'll see if that's the case. So, that's the axion story. That it's been a very fruitful endeavor to see why the past and future are so much in balance. Now, unfortunately, I don't have a clock, but I don't think I've spent too long. Anyway, I'll walk through one more story, the story of anyons. Since the discovery of wave-particle duality and its elaboration in quantum theory, we understand that the basic units of all forms of matter, including light, are the same sort of things. So you can call them wavicles or waves or particles, things that have both wave and particle properties. Let's just keep it simple and call them particles, understanding that they're different from classical particles. However, so that's very satisfying. It's a grand unification, if there ever was one. All kinds of matter have a common description. But when we consider the behavior not of single particles, but of groups of them, we find that this unity falls apart into two kingdoms, bosons and fermions. Bosons are collectivists, they like to do the same thing, or technically they like to occupy the same quantum state. And photons are bosons. A laser beam is an excellent example of bosonness in action. All the photons are the same color, moving in the same way, even coherent in phase, so they want to do the same thing. Fermions are individualists. They hate to do the same thing. Technically, they refuse to occupy the same quantum state. That's Pauli's exclusion principle. So it couldn't be more different. Electrons are fermions, and the solidity of matter is an excellent example of fermionness in action. Now, why is there this division? Well, you'll find in textbooks proofs of this based on the fact that if you exchange things twice, you have to get nothing. So you have to get no effect. So the only thing an exchange can do is give you a minus sign. But those proofs are fundamentally flawed. They work in 3 dimensions, but it turns out that really bothered me when I read this so-called proof as a graduate student. It's not a proof. And if you really analyze things, you find that in 2 dimensions, in flatland, things can get much more interesting. This is a case where less is more. The reason is closely related to the theory of knots. In view of the time, I won't be able to go into detail on this, but let me just say that in 4 dimensions, knots are not knotty. The reason is, if you think about 4 dimensions, and think about trying to entangle 2 strands, the question is, can you move one past the other? And in 3 dimensions, there can be a barrier to that. But in 4 dimensions, you can always move in another direction. Think of it as a temperature. You can make this hotter. If they're the same temperature, you can make this guy hotter, move it through, cool it back down, and there's no way of entangling it. So if you apply that not to world lines, you see that world lines of particles can't get knotted in 3 + 1 dimensions, but they can in 2, and that makes richer possibilities. So I named these new kinds of particles anyons in the spirit of anything goes. Of course, not anything goes. There are strict rules, but they can have a lot more than fermions or bosons. And experimenters can construct a wide variety of 2-dimensional worlds. This is not just area speculation or mathematical exercise. It's the 2-dimensional worlds are also known as thin layers of material. So your computer chips are 2-dimensional worlds. In some of these materials, there are strange states of matter in which electrons fission, break up into anyons. For electrons, this can be a shattering experience. Here's a picture of an electron about to be broken up into smaller units. And these smaller units are no longer fermions, nor are they bosons. They obey different kinds of properties. And the properties, the remarkable thing is that anyons, unlike bosons or fermions, have a recollection of how they've been entangled in the past. They have, roughly speaking, memories. So they're much more powerful than bosons or electrons. Feeling their strength here. If you put a lot of them together, you can support a very rich collective memory. Concretely, what you find is that when you wind some around others, the wave function of the whole bunch of them changes in ways that keep a record of what you've done. So you get an elaborate memory that keeps track of how you've entangled things. This is the basis for something called topological quantum computing, which actually has cache value. Microsoft is investing heavily in pursuing this to make a new generation of computers with different powers. Here's the idea. You move particles around to change their wavelength. And then you can measure that has an effect. Print the memory by moving it around, and then you read it out by doing things, which I won't go into. This is what it actually looks like. You have different semiconductors and different states of matter. This was all going on at low temperatures, with superconductivity is involved, and edge states. It's all very intricate application of quantum mechanics, but the upshot is that there should be anyons at the two ends of this wire, and by manipulating the field, you can move them around in a circuit and get the quantum memory. So, I've shown you how twice now, in two examples, how very abstract and ambitious theoretical ideas about big questions lead, if you follow them out, into suggestions for experiments and suggestions for phenomena that I hope will be fruitful. So, to me, this is a wonderful process, like watching a baby grow up. So, thank you for looking at my babies.
What I propose is that you ask our guest whatever you think worth asking, without no constraint, without no nothing, and then probably prompted by your questions, we can also intervene in this roundtable. So, any young physicist is courageous enough to make the first question?
Must be young.
You're young enough. You're young enough. You're young enough.
Go ahead for it.
Well, there was a comment in Sheldon's question, talk, which I think was quite well put, and which I believe is something which is not so well recognized, namely the importance of Camlan in settling the solid agenda problem. Without Camlan, we will still be unable to know the origin of the explanation of the problem even today. And somehow that experiment was completely, to some extent, forgotten in the prizes.
Well, I think in general, make a more general comment, which is Professor Glashow showed a long list of Nobel Prizes, many of them multiple prizes. The people who do these things, who have to make these decisions, have a tough task often, and many very important contributions don't get recognized. But it's a reflection of the achievement of the standard model and everything associated with it, both in theory and experiment, that even though it's been so well recognized, still there are things that were worthy that didn't quite make it.
I think any of us can list dozens of accomplishments that deserved Nobel Prizes and didn't win them. This is true not just in physics, but in chemistry, biology, astronomy, etc. Just think of, for example, of Vera Rubin, who recently passed away, who was the person who basically discovered confirmed the existence of dark matter in general present in galaxies. A wonderful physicist, astronomer. There is no Nobel Prize in astronomy.
So, which young physicist was? Yeah.
So, as you will know, LHCb has some present anomalies which appear to violate electron universality, and I wanted to know if, because this seems to spoil the idea of unification, and if this can be reconciled or they are incompatible. The universality violation and the idea of unification.
Didn't quite understand.
He's alluding to some experimental hints from LHCb that there's violation of lepton universality. And what would we do about that?
You have a paper about that.
It is true. Look, is there new physics up there at high energy? Is there a great desert extending many powers of 10 beyond the reach of the LHC or not? And we do not know. But even if there are particles presently out of reach, they might induce small effects, such as flavor change in neutral currents. And therefore, I'm very, very strong advocate of experimenters looking for these effects. And of course, these experimenters don't need any such encouragement. They know full well that would be one of the most exciting discoveries they could possibly make. Do I expect flavor change in neutral currents to be discovered? I think there's a good chance.
It's more than that. It's lepton non-universality as well.
Lepton non-universality is another issue. Again, if there is a lepton non-universality, then as I argued, and many people have either supported me or disagreed with us, if there is a lepton non-universality, I would expect there to be a lepton flavor violation as well. It is the most natural possibility. To avoid that is difficult.
I think, although I haven't seen this paper, I suspect that most theorists would react to this not by tinkering with what I call the sacred principles of the standard model, but by adding additional structure. So it would be pointing to some new world, not upsetting the overall picture of ordinary matter, which we've really confirmed in great depth, and it's very, very hard to see that unraveling, although in principle it's good.
No, it's easy enough to introduce additional structures that are compatible with everything you hold sacred.
Any further questions? And I'd like to then follow up on the axion story. So, where dark matter is one of the most intriguing things around. There's a few things where we really have something that we haven't explained yet. WIMPs, we know, have motivated a lot of experiments, and those will pretty much converge on an answer in the next 10 years. Is the case as good for axions? Can you map out the parameter space in a few decades and answer that question? Or?
The central ideas of axion physics lead basically to a one-parameter theory that is pointing to an overall scale. There are possible complications, but they're relatively small. So it's essentially a one-parameter theory. And as far as the interactions are concerned, the properties of this particle, the mass, and so on, I think we can be pretty definite about that. What's much less, to me, much less firm is the cosmology. So if you are, because it's very, very early universe cosmology where these particles get produced, and we don't have a lot of experimental information about that. If you make a straightforward extrapolation of what we know about cosmology, you can estimate what the background is going to be like. And if you do that, I think one can be pretty optimistic that experimental ideas now on the table will explore the full, plausible, one-parameter range of theories over the next 10, 15 years, something like that. It's underway. As you saw, there are people determined to take up this opportunity. And on the other hand, one reason why axions are rising in popularity is that the WIMP searches have already gone on for a long time and explored most of what was thought to be the plausible parameter space, and don't have much more to go before they run into irreducible backgrounds. So axions, to me, were always a very plausible source of dark matter, and the competition has become weaker over the years.
And I think people are looking for alternatives now.
Yeah.
Maybe in the next 10 to 15 years we can settle it.
Well, in that context, could I add a word, basically a question? Our cosmology that we have has perhaps more open questions than our particle physics, and one of them has to do with the strange coincidence that the amount of dark energy is of the same order of magnitude as the amount of dark mass.
Yeah.
And one of our colleagues who has addressed himself to that issue is Eric Verlinde, with his notion of, what is it called, emergent gravity. And I can't understand his papers, but I'm wondering what Frank's opinion is, or anybody else's, about that particular direction, which claims to link dark energy and dark matter.
Well, Eric is a friend, and it's certainly worthy of exploration whether dark matter is not really a form of matter. It's some unexpected modification of gravity. The actual ideas that he sketched out are very sketchy. They're not a fully elaborated theory. There's a lot of hand-waving. To me, if you interpret the words literally, they run into phenomenological problems, like with that bullet cluster I showed you. Very hard time reconciling his framework with observations. It also does not address at all the fact that dark matter is not only responsible for these galactic rotation curves, but also for effects in very early universe cosmology, and his framework can't address that at all. So there are a lot of things that that dark matter as matter explains that his framework, at least so far, does not explain. They would all have to be coincidences. So I think it's, I wish him luck. Actually, I don't wish him luck, but you'll need luck in order to promote that into a fully fleshed out account of reality. More generally, I would say that Einstein's theory of general relativity is very, very difficult to modify in a consistent way. The dark matter really looks like matter. It forms halos around galaxies. It's not evenly distributed. It's produced, its density inferred from that also matches what you get by extrapolating matter back to the Big Bang and get the critical density. So there's a lot of things that hang together if you imagine that the dark matter is particles, either WIMPs or axions or potentially some other kind of particle that you need to really, that would just be coincidences somehow, misleading jokes on the part of God. If there's some basically different explanation somehow modifying gravity.
I have a very simple question. So the standard model has turned out to be an incredibly successful theory. But ever since it was created, there has been a feeling, even with the founders of the standard model, that there is more to new physics than just standard model.
Yes.
And we have searched and searched since then, and there is no significant hint of new physics apart from neutrino and dark matter, which can be probably easily reconciled with the standard model without changing the fundamental things in a very deep way. So I was just wondering that given the status now that LHC has not seen anything significant and we have kind of reached the experimental stalemate, which new theory proposals do you think, in your opinion, should deserve a more concentrated effort as of now, and which should be maybe put on a back burner for the time being?
Well, I'm not going to, since I'm going to be improvising this answer, I won't suggest anything be put on the back burner, but certainly some promising kinds of experimental directions that could shed new light on fundamental questions include, of course, pursuing the LHC program to the end, looking for fundamental electric dipole moments of particles, looking for rare decays, looking for cosmological relics that might include, for instance, cosmic strings, looking for the variety of axion signatures that I showed you. Axions are certainly, and other dark matter searches are certainly important. I mean, the dark matter is there. I mean, it's a phenomenon, okay? It probably is matter, I think. So there's some new form of matter to be observed. By the way, I should emphasize that it's by no means peculiar to think that we introduce a new form of matter that you only see gravitationally. I mean, for a long time, neutrinos were a postulated form of matter that hadn't been seen, and they, in fact, are a form. They contribute significantly to the cosmological density of matter. So that's a very natural consequence of our framework. I don't know, you probably think of others.
It's hard. It's very times right now are somewhat frustrating because before the discovery of the Higgs, people my colleagues had divided into various groups, some of which said that there would be no Higgs and nothing to be discovered at the LHC. Others said there would be multitudes of things to be discovered at the LHC. I was one of those enthusiasts. Other people said there would be the Higgs boson and nothing else. And those people turned out to be, at least for the moment, right. This has been fairly distressing. Therefore, many of my colleagues have gotten very enthusiastic about CERN's program for a 100 TeV machine, also 100 kilometers, and so have the Chinese become very excited. Many Americans have joined in that excitement. And both are thinking of building a super machine. And I think that will be, I think it will happen. I hope that it will happen, but unfortunately it's beyond the purview of today's graduate students to be concerned about it because it will not be available for a long, long time. That's scary and disappointing. Of course, meanwhile, the LHC will be much upgraded in luminosity, and perhaps the search for flavor-changing leptonic currents can be successful. That would be a big boost, and I would certainly hope that that research is pursued. Neutrinos have also turned out to be rather disappointing, since the clues that have occasionally arisen for something new in neutrino physics have consistently disappeared. I still hope that something beyond the 4 parameters that we have, 3 angles and a CP violating parameter, not yet measured, and 3 neutrino masses. I hope there is something beyond that. So far, there is no indication that there is.
Let me take this opportunity to mention that as we keep thinking and trying to improve on our understanding of the fundamental laws and make more beautiful, more compelling frameworks, more unified, new ideas crop up. So I'll just mention one that's emerged in recent work that I've been doing with Professor Valle and other people at Valencia, which is as a consequence of trying to unify not only the interactions following Sheldon Glashow, SO10, but also the families, an even bigger structure, as a remote consequence, but not so remote, but a consequence of following out those ideas. We suggest the possible existence of a new stable kind of matter that's maybe 10 TeV particles that they're stable but annihilate in pairs. So they're consistent with cosmology. They would be a subdominant component of the dark matter, possibly producible at accelerators. It's just an example of ideas that crop up that could point to very fundamental new physics. And I think proton decay, of course, I forgot to mention proton decay is another example. That should definitely be pursued more vigorously, because the existing limits are really tantalizing from the point of view of unification schemes. So I am always optimistic, but maybe foolishly so. I thought the LHC would find evidence for low energy supersymmetry, but proton decay and dark matter, maybe even subdominant contributions to dark matter. There are lots of possibilities, but it's, of course, it's much easier to dream up possibilities than to find them.
Let me, in connection to your answers, one of the main efforts that LHC will make in the next years, and also, one of the ideas of thinking of future lives is to exploit the Higgs physics. And from your answers, I have not seen that you have given, a big role to understanding better the physics of the Higgs.
Well, of course, it's important.
Will be important.
It could be. Yeah, the Higgs could be a portal into kinds of phenomena that you wouldn't have otherwise detected. Technically, it has a unique place in the standard model because it has couplings that are dimension 2, more open towards new physics than strictly renormalizable couplings that everybody else has. But in any case, yes, I think that's worth exploring. Unfortunately, the existing observations on the Higgs particle are just so consistent with an absolutely minimal implementation of symmetry breaking. It's a little, it was very surprising to me. I don't know about you. And so we're kind of, it doesn't point directly towards any direction that where we should follow up.
That also depends on the precision that you can
Yes.
measure. So
Yeah, of course.
at which level to really expect to have deviation.
Yeah.
So now I don't think that we are at that level.
Yeah, well, that's a good example of looking under the lamppost where there's light.
Well, the light is not yet turned on. The high luminosity LHC is not yet there, but it will be. Yes, of course, that is an important field.
Very important.
So I'm really curious about this concept of an axion atmosphere of black holes.
Yes.
And you said this is a kind of hair, and of course everyone thought that pair is a way of addressing the information paradox in black holes.
Yeah.
So can actions do something about the information paradox, or we need to look at gravity, pure gravity?
This does not address the information paradox, and really does not rely on, how should I say, the deeply mysterious aspects of quantum gravity. It does rely on, of course, quantum mechanical interaction between gravity and matter. But and there's a fascinating fascinating phenomenon called superradiance, which is related to Hawking radiation, which is responsible for creating these atmospheres. So, if it were found, it would be an extraordinary discovery that at the same time would confirm interesting phenomena about the quantum mechanical interaction of gravity with matter, the dynamical equations of black holes, the existence of axions, the reason why time reversal is so good, and the dark matter problem all at once. So, well, we'll see.
And the second one, now that we are getting closer and closer to the event horizon via the gravitational waves, or maybe the event horizon telescope, can we know something about these actions there, or they are just as difficult to detect as here on Earth?
I think they're even more difficult. but it's possible that further investigation will unearth characteristic signatures. I don't know of any offhand.
Well, something exciting is happening up there with the third discovery of colliding black holes, emerging black holes, because they're all so big, and that was entirely unexpected. And I also read that there's evidence now that large stars do not necessarily go supernova, but they collapse quietly, forming black holes. I wish the astronomers would, or the astrophysicists would confirm that this is a likely possibility. My feeling that astrophysicists don't really know what they're talking about is now confirmed by recent discoveries. Very exciting. Things are very interesting up there.
Yeah.
Someone from the other half of the room?
I have a question myself, if I may. Recently there was a paper saying that inflation is an untested and untestable hypothesis. And there was a strong answer to that paper, which, if I'm not wrong, you signed.
I did. I don't know if they do, should I? No.
It's not only that particular case, but in general, nowadays, physicists are throwing at each other face the untestable complaint. Do you think that in that particular case of inflation, they were wrong? That there are...
I signed that response with considerable misgivings, because I don't like the idea of ganging up on people who dissent from the sort of conventional accepted consensus wisdom. But the article in question in Scientific American by Lee, Abby Lee, and Loeb, and Paul Steinhardt, and another young researcher, I thought went much too far in dumping on inflation and saying there's no evidence, it's untestable and so on. But I think inflation is not a detailed theory on the same footing as the standard model, where you have mountains of evidence and very precise predictions, and if anything doesn't quite work, you get very upset. or very excited. Inflation is more of a broad framework. However, there are many things that could have gone wrong. It does make sort of semi-quantitative and qualitative predictions. It's not an empty vehicle. So,
Is there an alternative?
and there's no alternative. There's no real alternative. That's the other thing. So it's certainly suggested fruitful questions and guided research in ways that turned out to be well, fruitful, directly. And for instance, suggesting that there's a slope to the perturbations spectrum as a function of wavelength. That turns out to be a very good thing to ask, and it does seem to be a slope in suggesting that the total density of the universe should be exactly critical, or very close to it, which was not evident in the data at the time it was suggested, and so forth. So I would say it's way overstating things to say that inflation is an empty word that doesn't correspond to a fruitful scientific idea. I think it does. It needs improvement, but I think it's a good starting point. Shelley's made some smart actuality remarks about string theory. That's a bit different.
No, I wonder, will Steinhardt have any alternatives to suggest? I mean,
Yes.
like him.
Well, he is very fond of something called the ekpyrotic universe, which he's developed with Neil Turok, that hasn't won a lot of allegiance, but might be an alternative to inflation.
So you published, I think in 2006, a paper about gravity and the consequences of the coupling constants with gravity.
Yes.
Could you explain that, and if you are still interested on the topic, or?
Well, it means a little bit technical, but a very important element of our thinking about physics beyond the standard model and achieving a unified theory that Professor Glashow alluded to is the main quantitative aspect of that we can check, is that if you assume that the different interactions derive from a single interaction by symmetry breaking, then you can get quantitative relations among the strong electromagnetic and weak interactions that you can check against experiment, and they look pretty good. In detail, they only really work if you have supersymmetry or maybe some other modification of the simplest ideas, but they're close to working even in the most simple implementations of unification. So, but then the question arises, what if you include gravity? These calculations don't include gravity. Then the question arises, what happens if you include gravity? And there are two aspects of that. Does it modify the calculation significantly? I think basically, unless there's something drastically wrong with our understanding, no. but then there's another question, which is, does gravity unify with the other interactions too? Can you also account for the strength of gravity? And I don't think we answered those questions in that paper, but I do think they're important questions. And in general, the whole, people correctly, I think, for understandable reasons, emphasize that we have two powerful theories of nature, or two powerful ingredients of our understanding of nature, general relativity and quantum theory, which seem to come from different universes of ideas. One is about, they seem to come from different universes of ideas. And we've had a heck of a time even reconciling special relativity with quantum mechanics. I think the standard model now does that very, very well, but it required a lot of new ideas. But so general relativity is not there. So the search for phenomena and calculations that bring in quantum mechanics and gravity at the same time is very important, because there's very little experimental grip on that question. The scales don't seem to be right. The expected effects are very, very small, and so theorists can go to town talking and talking and talking about quantum gravity, but nothing ever comes out as far as experimental tests. So we have to keep trying.
The discovery of gravitational waves has started a new form of astronomy. The question is the possible links that it may have with our kind of particle physics, in particular whether the Big Bang could generate what kinds of gravitational waves, let's say in very early phase transitions, whether you have any ideas as to how that could happen.
Well, the LIGO experiment is not sensitive to cosmological gravity waves. Lisa will be, so that would be very interesting.
And Lisa,
A later experiment.
Lisa is coming, is it not approved by the European Space Agency?
Well, there's Lisa, yeah. Eliza, I guess. Eliza. Yeah, so that will happen. We'll get that, and as many of you probably know, a few years ago there was a purported detection of gravity waves from the early universe from studying the microwave background radiation. They would imprint.
That was embarrassing.
Yeah, it turned out not to be true, but it could be. But that's being further in that direction is certainly important to pursue, and it's going to be pursued with more accuracy. And now people realize that there's dust up there, and anyway, so that could be important. As far as the LIGO kind of gravity wave, that kind of wavelength and frequency range, they certainly could give us information in principle about black hole atmospheres, if there are exotic atmospheres like axion atmospheres. Eventually they'll give us information about the equation of state of neutron stars when you study gravitational waves and neutron star mergers, and that's interesting for QCD. And of course there's possible surprises that could point to new fundamental physics. So it's certainly important to keep an eye on that, not only for the fascinating astrophysics, but also for possible implications for fundamental physics.
Well, they will also be able to learn whether these double black holes were born double or result from one black hole catching another, and that's easily distinguishable by whether they have the same spins or not. And there is some indication, I understand, that in this third event, the spins might be in the opposite direction.
Yeah.
That would certainly be evidence that at least some of them are made individually rather than as pairs.
So for sure there'll be fascinating astrophysics.
Yeah,
So
that certainly can be acceptable. But it may not impact particle physics.
So the two things that we know which require some modification to standard model is neutrino physics, basically neutrino masses, and dark matter. So do you think that they might be intimately related with each other in some sense? Or it's just a coincidence that we have started scratching the new physics part from these two sides, and there might not be some.
I don't see any very direct relation. And I also do, I think the structure of the standard model poses many problems other than neutrinos and dark matter. For instance, why are there 3 families? What is that all about?
And by the way,
why
we don't know
the-
how neutrinos get their mass.
We don't really, yeah,
I mean, we have words for
why do the quantum numbers fit so well into a unified theory? Unless there really is a unified theory. Why is the theta parameter, this potential other source of CP violations or T violations, so small? So there are quite a, the standard model, for all its success, doesn't look like a finished product. It's got lots of loose ends and definitely could use some prettifying.
No, it's not a Tesla Model S.
Yeah, what is the experimental input that we can get in the next decade? So we know colliders are getting more expensive and further apart in time. And there are many other ways that answers could come from, I guess.
Yeah. Well, we already mentioned a few with proton decay experiments, I think are still important. Astrophysical experiments that look for strange things in the sky, dark matter searches, searches for electric dipole moments, those are laboratory experiments. Et cetera, et cetera.
Do you see any of these new probes or other probes than colliders and accelerators? Do you see them replacing, say, taking over the role that colliders had in the 60s and 70s?
No.
What can we ever do without them?
Well, I mean, we could, we as humanity, in principle, we don't need particle physics at all for practical purposes. But it would be a shame not to pass on this opportunity to expand our deep understanding of how nature works and learn some lot of fun things. There are many ideas about physics beyond the standard model that I think can really only be plausibly accessed by accelerators. And the one advantage of high energy accelerators is that they probe new ground that you might not have anticipated too. So I don't think we should abandon that direction easily.
Well, nor do I, but on the other hand, I'm very, very concerned that the time scale of the large accelerators may be enough to scare away people from accelerator physics. Right now, we have a community of people who are capable of building these accelerators. They may not be around when the next generation is available. Furthermore, and I say this in view of what has recently happened in my country, climate change, we cannot simply forget about climate change. If climate change becomes very apparent in the next 10 or 20 years, as it very well may, I think that the attention of scientists will be diverted. In fact, the attention of everyone in the world will be diverted. So we have a lurking catastrophe that we should all be aware of, and even if we are Americans, we have to try to do something about preventing the coal miners from going back to work.
In a sense, that is, but America is also leading the world in that respect. It's the first continent to abandon colliders, maybe. Is that
Would you think of march backwards?
Do you see the U.S. program? I mean, they have a very interesting program in many other ways, of course, but a big collider on U.S. soil, is that still something that might happen?
seems, will there be a big collider on U.S. soil in the foreseeable future?
No,
I'm not very optimistic. I'm not very optimistic.
no, because they've announced that we are now addressing the high precision frontier.
It would require a major course change.
And how do you see the participation of the U.S. in the international projects outside the U.S.? Can we imagine one day the U.S. being members?
Well, we can imagine, yeah.
Member is not just more than usual.
Well, that's a kind of political decision, but in general, let me say, I mean, call me naive, but I hope and I believe that the U.S. will awaken from this nightmare and come back to its senses more broadly. So pursue its scientific destiny, treat its not so wealthy people better, and make life easier for people, and welcome people from around the world.
Yes.
I just hope that'll happen. Yeah.
Okay. So maybe we should. There's another question. Sorry.
Coming back to the dark universe, you said that dark matter doesn't look like a modification of molecule.
Yeah.
But what about dark energy?
Well, dark energy does look like,
Or just a cosmological?
looks very much like an ingredient of general relativity that was there from the beginning, so-called cosmological term, which Einstein introduced reluctantly. But from the point of view of modern physics, it's the most natural thing in the world, except that it should be much bigger. It should be much more. And that's a very interesting problem. I don't think there's a really convincing consensus on why it is so small, but that's but the existence of dark energy is not a problem. It fits very, very smoothly into general relativity.
Okay, since we have been talking about the future, the situation is not easy, neither in the States. Next year, Europe is going to launch the discussion for what will be the future of the strategic of new machines and things like that. This is going to be a very, very difficult discussion. The main question is where the new physical scale lies. So my question is there any expected theoretical breakthrough that can give us any light in this direction?
Well, I would have said a few years ago with more confidence, but I would still say that there's strong circumstantial evidence for and considerable motivation for low energy supersymmetry. So that points to a not very distant energy scale. So that for accelerators, and then there's the dark matter searches, there's proton decay, there's electric dipole moments, all of which are plausibly existing just beyond the limits of current experimental
There was a great deal of discussion of just this in the late 1980s and early 1990s, and the Americans came to a very well-considered decision that the ideal energy would be the energy of the American superconducting supercollider.
Yeah.
That, of course, didn't happen. So fortunately, the Europeans bailed the world out, but the limit to their energy was compromised. It was not anything near what the supercollider could do.
Yeah.
Which is why we are back to considering an upgraded American supercollider, both in China and at CERN.
Yeah.
Let us hope that one of them, and one would be enough, is built.
Yeah. So, that kind of idea, and more generally, ideas for addressing the so-called hierarchy problem, or the source of electroweak unification, symmetry breaking. If it's not simply a fundamental scaling field, that could be, I think, definitively answered with a machine that's not vastly larger in energy scale than the LHC, so buildable.
A factor of 7.
Factor of a few, yeah.
Is there another urgent question? I think we should close the discussion here.